Welcome back. Now I want to introduce you to another way to describe a vector. Again, this is our A vector here, but instead of describing it with a vector magnitude and the three coordinate direction angles that we had here, alpha, beta, and then gamma, I can instead describe it with a vector magnitude A and two angles, theta, that goes from the positive x-axis until this A apostrophe, and phi, which goes from the positive z-axis until your A vector. In fact, this system is called the spherical coordinate system. And remember, you have 90 degrees here and also here. Here again, you have some rules to consider. The angle theta always starts from the positive x-axis and rotates towards the positive y-axis according to the right-hand rule. And then phi always starts from the positive z-axis. The theta angle has no limitations in terms of how it ranges. So theta can go from 0 to 360 degrees, but phi can only go from 0 till 180 degrees. So this is how it ranges. If you choose this system, then the following relationships can be derived. Since you also have a right triangle here, so you have 90 degrees here, you can say that AZ equals A times cosine phi, and then A apostrophe equals A times sine phi. If you look at this right triangle, then it makes sense. A times sine phi will give you this distance, which is your A apostrophe. Then AX equals A apostrophe times cosine theta. Again, it makes sense because this is a right triangle. This is your A apostrophe times cosine theta will give you AX. And then AY, that's A apostrophe times sine theta. That would give you this distance here, which is your AY. However, you know what your A apostrophe is. It's this one, A times sine phi. That means that AX equals, and instead of A apostrophe, I'm going to write A times sine phi, and then times cosine theta. And then here I will have AY equals A times sine phi times sine theta. So you have your AX, AY, and AZ. And now you already know that A vector equals AX times I plus AY times J plus AZ times K. And now we will replace AX, AY, and AZ with these expressions. So A vector equals, that's my AX times I, that's my AY times J, and that's my AZ times K. But remember, in the previous video, when we worked with our coordinate direction angles, then A vector also equals A times cosine alpha times I plus A times cosine beta times J plus A times cosine gamma times K. And so that means that this thing here equals this thing here. And then this thing here, it equals this one, cosine beta. And cosine phi equals cosine gamma, which actually makes sense because phi and gamma are defined exactly in the same way from the positive z-axis. So actually, phi equals gamma. And so now you can see how coordinate direction angles, which was one way to describe the direction of a vector, and then the spherical coordinate system, which is another way to describe the direction of a vector, Now you see how they are connected to each other. You see how they are related to each other. And there you go. Now you have all the tools you need to solve the problem that we started with. In this problem, this is what you need to do. First of all, you need to find gamma. You need to find this angle here. This is a coordinate direction angle. Then, what you need to do, you need to decompose f1 and f2 vectors into their I, j, and k components. Then you have to find the resultant vector of f1 and f2, so you have to add them up, and then you have to find the coordinate direction angles alpha, beta, and gamma for the resultant vector fr. So these are the 4 things that you have to do. And with the information I've given you so far, you can do it. So try it out yourself first, and then check the solutions in the next video. Thank you very much. Welcome back. So let's now solve this problem. Your first task was to find gamma. From the previous videos, you learned about this relationship. Cosine alpha squared plus cosine beta squared plus cosine gamma squared equals 1. This was a very useful relationship when you knew 2 angles and you had to find a third angle. And that's the case here. You know alpha and you know beta and you have to find gamma. So I can write cosine squared gamma equals, and then I can rearrange this equation like this. I can replace alpha with 45 degrees and beta with 60 degrees. Then I can take the square root of this equation, and that means that this 2 will go away, and so I will have cosine gamma equals plus minus 0.5. You have plus minus here because if you take the square root of something, for example, square root of 4, then it equals plus minus 2, meaning that 2 squared equals 4, and minus 2 squared, it also equals 4. Since coordinate direction angles are always defined from the positive x, y, and z axis, and all these 3 angles, they vary from 0 till 180 degrees, you have 2 options. Either your gamma equals inverse cosine, and then you put here 0.5, that will give you 60 degrees, so that's option 1. And option 2 is inverse cosine minus 0.5, that's 120 degrees. Since gamma is defined from the positive z-axis, then in this first case, this vector f2 would have a positive z component, and in this case, this vector f2 would have a negative z component. And so from the image, you can see that this vector f2, it has a negative z component. You can see that it points down from this xy plane. This is f2z here. It's negative. Because of that, the correct option for us is this one, gamma 2. So gamma equals 120 degrees. That's your first answer. You have found your gamma. Next, what we have to do, we have to decompose f1 and f2 into their I, j, and k components. Let's start with f1. In the previous video you learned about an alternative method to describe the direction of a vector. You learned about the spherical coordinate system. You had the magnitude of your vector, then you had a phi angle here that was defined from the positive z-axis, and a theta angle that was defined from the positive x-axis, and which rotated towards the positive y-axis. And so you could represent your vector like this. This was your I component, this was your j component, and this was your k component. So I can say that f1 vector equals the magnitude of F1, which is 450 newtons, times this expression times I, then plus the magnitude of F1 times this expression times J, and plus the magnitude of F1 times cosine phi times K. Note that these angles here, 30 degrees and 45 degrees, they are not the correct angles for this formula. First of all, the phi angle is defined from the positive z-axis, so this is your phi. And then theta is defined from the positive x-axis, so this is your theta. In this image, you can see that phi plus 45 degrees will give you 90 degrees. So you can say that phi equals 90 degrees minus 45 degrees. That means that phi equals 45 degrees. Here it's the same, but let's say if instead of 45 degrees you had here 30 degrees, then your phi would be 60 degrees. So be careful with that. And then your theta equals 90 degrees plus 30 degrees. So theta equals 120 degrees. And you can see that in this image. 30 degrees is defined from the positive y-axis, but theta needs to be defined from the positive x-axis. And you have 90 degrees between the positive x and positive y-axis. Just like with phi, you had 90 degrees with this xy plane and then the positive z-axis. And so now you have the magnitude of F1, you have the phi angle, and you have the theta angle. So the x component of this F1 vector is 450 times sine 45 degrees times cosine 120 degrees, and that equals minus 159 newtons. Then the y component is the following: 450 times sine 45 degrees times sine 120 degrees, that's 276 newtons. And finally, the z component is the following: 450 times cosine 45 degrees, that gives you 318 newtons. That means that F1 vector equals minus 159i plus 276j plus 318k. You have decomposed your F1 vector. And you can see that it makes sense because it has a negative x component, a positive y component, and a positive z component. And you see the same thing in this image. Negative x, but positive y and z. And now we have to decompose our F2 vector. Here we used the coordinate direction angles, alpha, beta, and gamma. From the previous videos, you know that using the coordinate direction angles, you can decompose your vector like this, with this lower formula. A times cosine alpha, that's the x component, a times cosine beta, that's the y component, a times cosine gamma, that's the z component. And so I can write F2 vector equals F2 magnitude times cosine alpha times I, F2 magnitude times cosine beta times j, and then plus F2 cosine gamma times k. So the x component is 600 times cosine 45 degrees, that's 424 newtons. Then the y component is 600 times cosine 60 degrees, that's 300 newtons. And then this is the z component, 600 times cosine 120 degrees, that's minus 300 newtons. So F2 vector equals 424i plus 300j minus 300k. And that's it, we have decomposed our F2 vector. Again, visually you can see that it makes sense because it has a positive x and y component and a negative z component. And that's what you can see in this image. You have positive x and y, but negative z. Welcome back. So now that we have decomposed our F1 and F2 vectors into our Cartesian ij and k unit vectors, we can now solve for the third part, which is finding the magnitude of the resultant vector that is composed of these two vectors. And since you have your ij and k components here, it's very easy to obtain your resultant vector. It's f1 plus f2. So fr equals this vector plus this vector. First I add up the I components, minus 159 plus 424. Then I add the j components, 276 plus 300. And then I add the k components, 318 minus 300. So fr equals 265 times I plus 576 times j plus 18k. And that means that the magnitude of fr equals 265 squared plus 576 squared plus 18 squared. And then I square root it, so I have 634 newtons. And now finally, we have to find the coordinate direction angles alpha, beta, and gamma for fr, for this vector here. From the previous videos, you know that if you have a vector that we called A, then cosine alpha equals the x component of that vector divided by the magnitude of that vector. Similarly, cosine beta equals the y component of that vector divided by the magnitude of that vector. And then cosine gamma equals the z component of the vector divided by the magnitude of that vector. You have the x, y, and z components of the fr vector, and you also have its magnitude. So you have everything you need to calculate alpha, beta, and gamma for fr. Cosine alpha equals 265 over 634. Cosine beta equals 576 over 634. And finally, cosine gamma equals 18 over 634. And so that means that alpha equals, you take the inverse cosine of that ratio, and you get 65.3 degrees. Then beta would be the inverse cosine of this ratio, that gives you 24.7 degrees. Finally, gamma equals inverse cosine of this ratio, and that's 88.4 degrees. And so we can try to visualize that vector. This is its x component, 265. Then this is its y component, 576. And this is its z component, 18. And so your fr vector ends up being somewhere here. Then this would be alpha, which is 65.3 degrees, which also visually makes sense. Then this would be beta here, which is 24.7 degrees. Also visually, it makes sense. And then finally, this is your gamma, 88.4 degrees. It also visually makes sense because it's almost 90 degrees. You can see that you have a very small z component. So this vector, it almost lies on the xy plane. If this vector had been on the xy plane, then gamma would have been 90 degrees. But it's almost 90 degrees, 88.4 degrees. And so now you have seen 3 ways to represent vectors in 3D. Using unit vectors, the magnitude of a vector, and 3 coordinate direction angles, and then the magnitude of a vector, and then theta and phi, and this is the spherical coordinate system. Thank you very much. Welcome back. Here I want to make an additional comment about vectors. We are all trained to think that a vector has a magnitude and a direction, and that's not wrong. However, in reality, a vector is a more general concept. A vector is a table with one column or with one row in which you organize information relevant to you. For example, in one of my autonomous car courses, I need to keep track certain things about the car relevant to me, so that I could build a controller that allows the car to autonomously track a trajectory on this XY plane. I have to keep track of the car's longitudinal velocity. That's the velocity that you have in the direction of your car's motion. Then the car's lateral velocity, even though the car's lateral velocity is a lot smaller than its longitudinal velocity, you still have it a little bit when the car turns. It might be very small and you don't feel it, but it's there. Then I also have to keep track of the car's yaw angle and also the change of yaw angle with respect to time. And then I also have to keep track of the car's X position and the car's Y position on this XY plane. And so I put them all in a vector. I'm going to call this vector X arrow, and I'm going to put all these quantities inside this vector. Small x dot, small y dot, psi, psi dot, big XC, big YC. In control systems, this kind of vector is called a state vector. And as you can see, it's a 6-dimensional vector. You have 6 rows, 1 column. You have 6 dimensions here. So you can't really visualize it, but you don't have to. In this context, this vector is just a table. This state vector is still a vector, but in a more general form. It doesn't make sense to calculate its magnitude nor direction here. If you do something like this, then you will get some kind of number, but it will have no meaning. Here, a vector is a table that contains relevant information about the car, information that you need in order to control it. I'm telling you this as a side knowledge. In this course, that's not the case though. Vectors in statics problems do have magnitudes and directions. And now let's solve some more vector problems. Thank you very much. Welcome back. Here I have another quick force exercise for you. So this is your XYZ Cartesian coordinate frame. This is your F1 vector, whose magnitude is 180 newtons. I have one angle here, which is 60 degrees, and then another angle here, which is 15 degrees. Then you can see that here you have a right triangle. And then here I'm going to draw another vector, F2, but its magnitude is unknown. And so from the positive x-axis, I'm going to define alpha, from the positive y-axis, beta, and from the positive z-axis, gamma, and they're also unknown. And so you have to calculate F2 and then these 3 angles, but 2 times. First of all, what are F2, alpha, beta, and gamma if the resultant vector Fr equals 500 newtons in the positive x direction only? So your Fr, it only points in the positive x direction and the magnitude is 500 newtons. So that's the first case. And then the second case is this. What are F2, alpha, beta, and gamma if Fr vector equals 0 vector? So this is what you need to calculate. Try solving it by yourself first, and then I'll show you how I did it. Thank you very much. Welcome back. Let's now solve the first case. What is F2 and what are alpha, beta, and gamma if your Fr equals 500 newtons in the positive x direction only? It means that the Fr vector equals 500i plus 0j plus 0k. And the other thing is that the angles that we have for our F1 vector, they are not official angles for the spherical coordinate system. For the spherical coordinate system, we are going to define angle theta that goes from the positive x direction and angle phi from the positive z direction. But of course they are very easy to calculate. You have 90 degrees between the positive x and y axis, so theta equals 90 degrees minus 60 degrees, and that would be 30 degrees. And then phi equals, you have 90 degrees between the positive z-axis and the xy plane, and then to that you should also add 15 degrees. So 90 degrees plus 15 degrees equals 105 degrees. So for the f1 vector, the I component, it will be f1 times sine phi times cosine theta. So it's 180 times all this. That gives you 151 newtons. Then the j component is f1 times sine phi times sine theta. So it's 180 times all this, which gives you 86.9 newtons. And then finally, the k component, that's f1 times cosine phi. It's 180 times cosine 105 degrees minus 46.6 newtons. And now, for the resultant vector fr, in the I direction you have 151, which is this one, plus the x direction of the f2 vector, and that needs to equal 500 newtons, which is here. So you're adding up the x components of your f1 and f2 vector. But of course you don't know your f2 vector, so this is your unknown variable. And then in the j direction, you have this one here, 86.9, plus f2y, and that must be 0 newtons, this one here. And then this is the k component. We have this one here, minus 46.6, plus f2z, and again that equals 0 newtons, which is this one here. So from here I can calculate my f2x, which is 500 minus 151, that's 349 newtons. Then f2y equals minus 86.9 newtons. And f2z equals 46.6 newtons. And so you have your three components for your f2 vector. And now the magnitude of f2 vector, that's just this 3D Pythagoras theorem, and that gives you 363 newtons. And then you calculate the coordinate direction angles like this. Cosine alpha equals 349 over 363, so it's this one over this one. Then cosine beta, that's minus 86.9 over 363, so that's this one over this one. And cosine gamma equals 46.6 over 363, so that's this one over this one. That means that alpha equals 16 degrees, beta is 104 degrees, and gamma equals 82.6 degrees. You just need to take the inverse cosine here. And that's it, we have solved this part of the problem. Welcome back. So let's now solve the second part of the problem. You still have to calculate the magnitude of f2 and then alpha, beta, and gamma, but now fr equals a zero vector, which means that you have 0i plus 0j plus 0k. Now you already know that f1 vector equals 151i plus 86.9j minus 46.6k newtons. And that means that in the I direction, we have to have 151 plus f2x, and that must equal 0 now. Then in the j direction, you have 86.9 plus f2y, it also equals 0. In the k direction, minus 46.6 plus f2z, that gives you 0. So f2x equals minus 151 newtons, f2y equals minus 86.9 newtons, and then f2z equals 46.6 newtons. The magnitude of f2 equals the 3D Pythagoras theorem, and you get 180 newtons. Then cosine alpha equals minus 151 over 180. Cosine beta equals minus 86.9 over 180. And cosine gamma equals 46.6 over 180. And so that means that alpha equals 147 degrees, beta equals 119 degrees, and gamma equals 75 degrees. And that's how you solve these kind of problems. Thank you very much.